Assalamualaikum and hi. My name is Muhammad Haikal Zikry and I will start this presentation by sharing a little bit of the introduction of our project. So our project is called Smart Jacket for the Blind, and the main purpose of this project is to improve independent mobility for visually impaired individuals by giving them better awareness of their environment. What makes our project different is the smart jacket is wearable, lightweight and also hands-free, unlike canes or handheld devices. This makes navigation feels more natural and less tiring. As we move forward, we will explore this project in more detail and highlight how this jacket works to support the visually impaired community. As you know, visually impaired people often face significant challenges when navigating both outdoor and indoor spaces. Traditional aids such as the white cane or guide dogs provide some support but come with limitation. For example, a cane can only detect obstacles at ground level and does not provide any object recognition. Meanwhile, guide animal can be very helpful, but they are expensive and not easily available to everyone. This highlights the need for modern assistive technology that goes beyond these traditional tools, something that can combine sensing, live feedback, and also monitoring to make navigation safer, more effective, and more accessible. Traditionally, navigation for visually impaired relies on three main aids. First, they use a white cane. It only can find obstacles on the ground and has a short range. Second, some use a guide dog. Dogs are helpful, but training them is very expensive and not many are available. Third, there is help from other people, but this makes the person less independent. And the problem is, these methods don't give real-time awareness of the surrounding or allow caregivers to monitor remotely.
So now we will be talking about the problem statement. So existing assistive technologies for the visually impaired often lack some kind of integration, sensing, and also remote monitoring capabilities, which would leave gaps in safety and independence. The current existing solutions mostly focus on ground level obstacle detection, but they fail to address stuff like collisions with upper body obstacles such as signboards, shelves, or even hanging objects, which will pose serious risks. Secondly, the difficulty of navigating in unfamiliar environments where users may lose orientation and even struggle to move. Next would be the limited caregiver oversight, as families or guardians have no sort of way to monitor them real time. And finally, the dependence on bulky and handheld devices, which of course would reduce comfort and also limits hand-free navigation for the user. So, what would be our solution for this problem? Simple. A smart jacket with integrated camera and live feed. Alright. So to briefly explain what it does, first of all, it has an ESP32 Sense camera which is mounted on the jacket, which captures the user's surroundings in real time. The ESP32 Sense runs a library object detection model trained which would be trained in each impulse and outputs both the object name and its relative position. So let's say there is a chair on the left. So the sound output would be chair on the left. So the user will know that there is an object on the left and to avoid it. Alright, moving on. It also has audio navigation assistance, which means that detected objects and positions are transmitted to a Raspberry Pi 3B Plus via UART, and the Raspberry Pi converts these text to speech alerts, such as chair ahead, so that the user will know that there is an object ahead of them, as previously mentioned just now. Also, the ASP32 streams a live video feed to the Wi-Fi via Wi-Fi to a custom-built Android app, which will enable caregivers to remotely monitor the user's environment for added safety. Then, finally, all the components are integrated into a wearable jacket system with a compact rechargeable power supply, which allows users to move more freely without holding any kind of handling devices. And at the same time, it is way more comfortable for them as it is wearable. Right. As for the objectives of the project, it is listed below here. So, first of all, We would be developing a wearable camera-based system by integrating the ESP32S3 Sense module into a jacket for continuous environment capture. Secondly, we will be implementing real-time obstacle detection using a lightweight AI model trained in edge impulse, capable of identifying objects and estimating their relative position. Next, we will be also providing an audio-based navigation assistance by transmitting detection results to a Raspberry Pi 3B Plus board, which converts object position text into speech alerts for the user. Also, we will be enabling remote caregiver monitoring through an Android application that streams the live video from the ESP32 camera, which ensures real user safety in real time. Last but not least, this project also ensures portability and hands-free operation by designing a compact, rechargeable, and comfortable power supply system which is integrated into the jacket. Now, as for the design thinking part, the first one would be sensing. And under sensing, the ESP230, the ESP32S3 Sense would act as the primary sensor. What I mean by this is that it acts as the eyes of the system, which captures the real-time video of the user's surroundings. How? We would train the AST, we train the bot using a lightweight ML models via edge impulse so that it would be able to detect and also label the objects. This will provide object type and also relative position. Example, chair on the right of the navigation path. And also finally, since it's hands-free and wearable, it ensures continuous sensing without the need for any kind of handheld devices.
I'll be cover the object detection subsystem. This is basically the brain that interprets what the jacket says. We use the ESP32 S3 Sense with its built-in camera to capture frames, and we train models in Edge Impulse Studio. The focus is on objects that actually matter to visually impaired users like doors, stairs, or any obstacles. The models are optimized to run directly on the ESP32, so detection works offline, so no internet required. When an object is detected, the system send alerts and even adjust the audio intensity depending on how close the user gets.
In our design, we use a camera with ESP32S3 to scan the path in front of the user and detect obstacles. Next, the system estimates the distance of the obstacle. For example, it can say obstacles 2 meters ahead. The jacket is connected to an app that gives audio feedback like turn slightly left or clear path ahead. Finally, instead of only warning about obstacle, the system also suggests the safest walking direction, such as move right to avoid obstacles.
Moving on, I will explain the last subsystem, which is the data transmission and visualization. First, the ESP32S3 stream video over Wi-Fi directly to the mobile app. This allows the user to see a live camera feed in real time. Secondly, the Android app, which we developed in Android Studio using Java or Kotlin, handles the visualization. It will display the live feed from the ESP32 clearly on a smartphone. Finally, for the UI, the Raspberry Pi provides voice feedback. Whenever an obstacle is detected, the Pi alerts the user with a spoken message, for example, obstacle ahead or zebra crossing approaching. This way, the system combines video streaming and audio feedback to give the blind user both situational awareness and safety guidance. This is a system block diagram of Smart Jacket. The ESP32S3 is the core device that performs object detection using edge impulse. It also acts as a live feed camera which continuously streams video. Besides, it also sends alerts over UART whenever an obstacle is detected. We choose UART for communication between ESP32 and the Pi because it is simple, lightweight, and reliable, especially for transmitting small amounts of data like event alerts. UART is more efficient and easier to implement compared to other heavy protocols. The Raspberry Pi 3 acts as the receiver of the UART messages. When it receives an alert, It converts the signals into audio messages using text to speech, so the user is informed in real time. At the same time, the ESP32S3 streams the live video feed over Wi-Fi to the smartphone app. This app visualizes the environment and helps with monitoring. Finally, the audio output from the Raspberry Pi is sent to an earphone, giving the user immediate voice feedback to guide them safely. Let's take a look at the methodology. From week 1 and week 2, project briefing was conducted by the course coordinator. In the meantime, from week 1 until week 3, requirement gathering and user research was also conducted. Currently, for week 3 and week 4, we are conducting the system design and planning. From week 5 until week 7, we will proceed with both prototype development as well as the testing and iteration. The final integration will take place in week 7 until week 10. For the last two parts, which is the demonstration and evaluation, also the documentation and handover will take place during week 10 until week 12. Now, let's take a look at the tools and softwares for Smart Jacket. Firstly, we will use Seed Studio Xiao ESP32S3 Sense for object detection and live feed streaming. Next, the Raspberry Pi 3 will be used for receiving alerts and converting them into audio messages. To power these two devices, we will use a rechargeable battery as our power source. For training the object detection model, we will be using Edge Impulse Studio. For the Raspberry Pi, we will run Raspbian OS to handle the UART communication and for the text-to-speech. Next, we are going to use Arduino IDE to program the ESP32S3, and for the app, we will be using Android Studio. Finally, we will use VS Code for general coding and testing.
For the hardware, we chose the ESP32S3 Sense because it is compact, easy to wear, and already has a built-in camera. We also added a Raspberry Pi, which is very flexible for networking and works as our video streaming server. To make the system portable, we use a rechargeable battery so it can be used outdoors without relying on cables. For the software, we use Edge Impulse Studio, which helps us easily train and deploy machine learning models on small devices. We use the Arduino IDE because it is widely supported and simple for coding the ESP32. Finally, the Raspbian OS runs on the Raspberry Pi, giving us a stable Linux platform to handle video streaming and data.
We also had to check if the plan is realistic. We looked at four areas. First, team expertise. Each member is assigned a subsystem based on their strengths. Second, tool availability. Our hardware like Raspberry Pi, ESP32, and sensor are all available and testable. Third, timeline. We created a phase plan with subsystem testing first, then integration, and finally outdoor trials so we don't leave everything for the last minute. And lastly, risk mitigations. For example, if the ESP32 camera isn't stable, we can switch to the Raspberry Pi camera. If the app takes too long, we can fall back on a web dashboard. This way, the project is achievable within this semester.
Moving on to the next section would be risk mitigations. So, and as everyone is aware, every project carries a certain amount of risk, and it is important to prepare early so that we are able to mitigate these risks. So, first of all, the ESP32 camera might not be available for purchasing or could be out of stock. So the proposed workaround would be to use the Raspberry Pi camera on the Raspberry Pi Model 3B Plus board as an alternative. Secondly, the Android app development might take a longer time than expected or face any kind of technical hurdles. So the proposed mitigations are to start with a web-based dashboard which utilizes a browser live feed as a fallback. And secondly, we could use pre-built libraries such as MJPEG Stream Viewer to reduce the coding complexity. Finally, Finally, the last risk would be Wi-Fi streaming from the ESP32 camera may lag or fail. So the proposed mitigation would be to test with a lower resolution and frame rate to improve stability. Or if that does not work out, we could use a local hotspot or tethering device instead of relying on the public Wi-Fi.
From a business perspective, most existing solutions are insanely expensive. Devices like Ocam or WeWork cost several thousand ringgit, way out of reach for many people. Our jacket prototype, on the other hand, costs around 350 ringgit. That's a huge difference in affordability. And because it's modular, it can be upgraded over time with better sensor or AI features without replacing the whole system. The value proposition here is clear. For example, independence for users, peace of mind for caregivers, and accessibility at a much lower cost compared to the market. So to wrap it up, the problem we're tackling is that the traditional aids like canes, guided animals, and human assistance don't provide full awareness or any kind of remote monitoring. So our solution is the smart jacket, a wearable system that integrates sensing, object detection, live streaming, and audio guidance. It's affordable, portable, and practical. The key impact here is that it gives visually impaired users more independence while giving caregivers a real-time visibility. Thank you.